Hi there, I'm Audie Cash. Thank you for joining me for this Smart IAQ Project Builder overview video. This will go through the fundamentals, the basics of the indoor air quality procedure. This is appropriate for those that haven't used the procedure in a while. Or if you're new to it, this will give you some foundational understanding about how 62.1 defines a set of criteria that allow us to build a calculator to determine whether or not your design meets the requirements for the indoor air quality procedure. Essentially, the indoor air quality procedure is a prescribed approach that allows you as an engineer to select outdoor airflow rates in combination with air cleaners to deliver a healthy indoor air environment. That begins by understanding the basics of 62.1, which essentially state that within any space, the people, the furnishings, and even outdoor air build up within the space a set of contaminants that we need to address through air cleaning and dilution by using filtration and extraction technologies like carbon filters or particle filters to remove those contaminants. And in a balanced state, the contaminant buildup is managed by dilution and air cleaning to the point that we deliver healthy indoor air. The only real way we can know this at any given scale is to use a calculator to do that work for us. And by using ASHRAE generated data sets, we can build a calculator, as you see in front of you, that does this very, very efficiently. Maybe the best way to do this is to log into the tool. And once you log in, your projects will be here and your archive projects are here if you're interested. I'm just going to create a new project from scratch. So this is going to be called a basics project. If you want to follow along, I'll pause and let you do this as well. When you're done typing in the title, click Create Project. Now, within the project workspace, and this, by the way, is the only screen you really need to determine whether or not you have a compliant design. The rest of the pieces of this tool will help you create output and content for specification purposes. But for basic design, this is where you need to live, in the project workspace. First thing you need to do is locate your project somewhere geographically. This determines the outdoor air concentrations of contaminants based on the city that you're selecting or the nearby city for where this project will be built. It also determines the enthalpy and climate zone so that you can figure out how much tonnage reduction you get when you do the indoor air quality procedure. So in this particular example, I'm going to choose Atlanta, Georgia. And then within the tool and within the indoor air quality procedure, you now need to determine the type of ventilation system that you have. You have several options. If you have a centralized system where you're supplying air into a room and the exhaust air is being recovered either through the plenum or through a duct system and it gets cleaned and recirculated through a filter, that recirculation system where it mixes with outdoor air at the system is called a centralized system. In a centralized system, you're going to want to select air cleaners that work in a centralized way. In that case, we have a centralized option here for you under air cleaning. Now, you may also know that that system is not necessarily constant volume. It may be variable volume because you have VAV boxes throughout your project. If that's the case, select this. When you make these choices, the equations that determines the concentration in the breathing zone will be modified behind the scenes. We're not going to have you do all that math by yourself. It automatically gets selected based on your design choices. We'll come back to that. Let's pretend we have a very simple system where it's a 5-ton air conditioner with a compressor. Outdoor air is being mixed within the system inside the building, and it's being recirculated in the room through an air handler. In that case, it's going to be a constant volume system to make things simple for ourselves. That air handler is going to bring in outdoor air at a rate of whatever is determined based on my design, but typically that will be your choice as you do the design. As the air gets brought into the space, we need to choose a filter. We'll choose MERV 11. And we also need to determine the ventilation effectiveness for the space, which is going to be how well the air mixes. Ventilation effectiveness, or E sub Z, is whether or not the air comes in at a neutral temperature, whether it comes in at several degrees or 15 degrees higher than ambient temperature, so it doesn't mix as well because it rises along and stays along the ceiling. All of that's from a table in ASHRAE 62.1. Select your E sub Z appropriately. I'm using a decoupled system, so the air cleaner is completely independent of the HVAC system. So my 5-ton unit's going to run as needed, and then my air cleaner will run as needed because I'm selecting a decoupled system called GridSet. Now, I'm not going to go through the trouble of naming all my zones, but you can name them if you want. But within this room where I have a 5-ton air conditioner, the amount of outdoor air I need is based on the space used, or the occupancy category. In ASHRAE standard 62.1, there's a fairly lengthy table of all of your options. Those are presented to you here. Select the one that best describes what's going on in this room. Maybe the best case for this will choose a meeting room. So I'll start typing meeting. So maybe this is a conference room or meeting room in the middle of an office building. And the area is 2,500 square feet. I need to set my zone height. And then the default occupancy automatically populates here. This is straight from 62.1. Obviously, if you're doing this design, you know how many chairs are in the room or how it's being configured. So maybe this room really only holds a maximum of 80 people. Please enter that. And why that's important is because the first thing we need to do is understand the baseline, the ventilation rate procedure baseline. That's a rate of outdoor air per square foot and a rate of outdoor air per person multiplied and then divided by, or multiplied by area, multiplied by people. Those two numbers are added together and then divided by the ventilation effectiveness. And then if you have spaces several hundred feet above sea level and above that, you then have an accommodation for that through the air density correction factor, which is shown right here. So this is your VRP total VOT, your total outdoor airflow needed for this zone is 722 CFM. Now there's a blank here, and this is up to you. And this is where I think a lot of engineers need a minute to pause and think about this procedure. Inside this zone, we have air cleaning. We have 150 CFM of air cleaning. I then need to supplement that with some amount of outdoor air for dilution. As we remember, it is a balancing. It's a balancing of outdoor air and air cleaning. So in this particular case, I have several options. I could just enter a value, let's say 300. And that plus this with its performance, pass. And we'll look at what passing means in just a second. I could also choose to minimize that OA, that is to take it down to the lowest possible level that will still pass. Now, as a designer, you may need to think about this from the standpoint of, well, how much air do I need for my exhaust demands? How much air do I need for pressurization? How much air do I need to manage CO2? Well, all of those things are important. We can get into those in a little bit of detail, but know those values as your minimums, because you just accepting minimize OA may create other problems for you. Some people like to think about CFM per person. Maybe if I apply 7 CFM per 80 people, that gets me to 560 CFM in this space versus my design of the VRP 722, a nice savings. And this will provide a very comfortable indoor environment as well. And that's an appropriate approach. So as you can see, I'm bouncing around some very wide range of values, but these are all passing conditions. The next thing you can do is do a percentage of the VRP. Maybe your objective is to reduce outdoor air across your project by 55%. So by putting it as 55%, 45% of the VRP will allow me to reduce 55%. Choose that value, and now that number is plugged into your VOZ. It's a couple of different options. But no matter what you choose, what you're now doing is you're putting in balance contaminant generation in the space, outdoor airflow, indoor air cleaning. And what does that look like? You click in this calculator and you can see the indoor air quality procedure consists of these contaminant parameters, the outdoor concentration for my location in Atlanta, Georgia, the generation rate as provided by ASHRAE for this space type, the filter efficiency of my air cleaner, smartIAQ grid set, and the design limits from 62.1. By looking at these in balance and in steady state, you can see the concentrations of each individual compound in the breathing zone. None of those concentrations are greater than the design limit, so therefore they pass. In addition, you need to look at some in combinations where we look at the mixed exposure sum for upper respiratory, eye, and central nervous system. All of this straight from the standard, and the calculation runs in the background. So at this point, we know we have a compliant design because none of the parameters are greater than the design limit, and the mixed exposure sums are all less than 1. I mentioned CO2 before. You can look at what the CO2 model is for this space. Given this outdoor airflow reduction with a maximum of 80 people, at a total of about, it takes 5.5 hours to get to steady state. But once we get to steady state, the CO2 in this room will be 3,053, assuming no opening and closing of doors, 80 people are there the whole time. Sounds unreasonable that that would be the case. However, some people like to think about the 8-hour average. Imagine if you were in this room for 8 hours, your average exposure would be 2642. Maybe these values are something you want to adjust. We have a separate video on CO2 adjustment, but I'll show you real quick. Maybe I want to design to 1700 because that's a value that I understand from ASHRAE for these types of spaces is appropriate for demand control ventilation. I can calculate the VOZ and it says I need 679 CFM to achieve that, so I can hit apply. You'll notice the chart updates. So that's a maximum of 1700. I can save this value. Notice it updated it here for you. Save that value there for you. I can save this to the room. And now that's my new updated value. Okay. Not a very big savings at this point, but that's not here or there. I'm just giving you the examples and giving you the values so you can understand how this works. So now that I'm done, it has done all the calculations and has determined for a room of this size with this population, this amount of air cleaning plus this amount of outdoor air will give you a passing scenario. And as I said before, you can ratchet this value up or down knowing that that needs to meet your minimum ventilation requirements for pressurization, but also can be used to throttle up or down CO2 thresholds. One final point, and this is important, you can also modify the amount of air cleaners you have in this design as well. That can help you reduce the amount of outdoor air you need if you were starting to get borderline on that. And what we typically say is a grid set unit is good for 1,500 square feet. So this space would probably need two anyway, which would allow you to further reduce your outdoor air if you wanted to. I've put in 2 units, just so you know, I've put those 2 units in, and you'll notice your air cleaning capacity is now up to 300 CFM in a space of 2,500 square feet. So basics for the indoor air quality procedure. I hope you find this helpful. And as I say at the end of these videos, thank you very much for paying attention, and I look forward to hearing about your success with the indoor air quality procedure.